Hello everyone. Someone on YouTube contacted me about the CTEK battery charger. It's got two of them failed. You can see it says the smartest battery charger in the world, which is a very bold claim. It might be the most flashy lights, smoke and mirrors battery charger in the world, but they both failed, and it's a shame that it's not smartest and best designed electronics battery charger in the world. Then we wouldn't have to repair it, would we? So for the money, yeah. Let's have a look inside this thing and see what's going on with it, eh? So, a lovely bag. What have we got in here? There she is. The bag over there. So, we've got a bunch of clips. Plug-in adapter. You can put a charging support adapter, or I think there's a series of accessories, but clips together like that. Clip on your charging leads for your battery. Nice quality, good strong spring. Wouldn't want to put that on your finger. No, you definitely wouldn't want to put that on your finger. So yeah, the best clip I've seen. Very strong, nicely made actually, as you'd expect for the price, but not working. Not a peep apparently, not even the slightest peep. Let's plug it in and see what she does. Main's going in to the isolated main supply, and dead as a dodo. I'm guessing whoever it is has checked the fuse. Let's check the fuse. Not going to be the fuse, but I ain't going to bother buggering about with it just in case it is the fuse. You never know. So we've got a 13 amp fuse, which is wrong for this cable. Wrong fuse. So has it been changed, or was it supplied with the wrong fuse in it? We don't know. Should be a 3 amp really. The fuse in here is, this has got, if it's on a normal UK ring main, you've got 50 amps AC cable supply and 50 amps through this cable. We had a short at this end, the 13 amp fuse. This is like a 5 amp cable. So really the object of this fuse here is just to protect the actual line cord, the mains lead, because there's another fuse inside which protects the device. Okay, so if there was a dramatic short or a catastrophic short on here, it could burn the wiring out rather than blow the fuse. It would probably blow the fuse, but it's still not right. You know, according to safety standards, it should be a 3 amp. And stick it on the beeping mode, shall we? Yeah, so the fuse is good, so it's not that. So they've ruled that one out. So what do we need to take this apart? Is she all glued up, or what is she? Clipped together? It looks like someone's had a go, look, see? Can you see the witness marks where someone's had a chomp at this with a screwdriver? But to me that looks like that's been probably ultrasonically welding. There's a crack there as well. Has it been dropped, do you think? Otherwise she looks in good nick. I did a review on this. If you want to see how this works and how it charges and just how effective it is on this regen and all the rest of it, then have a look at the other video in the CTEK range. So there's a few other videos on this where I test it using the test harness and the software. But it's been chomped around, and has that been apart? Oh, it has, look. So that was easier than I expected. So is it welded or clipped together? Not sure. That looks like that's broken, doesn't it? It's broken off. Not sure what the mechanism is that holds us together. Glued, I think. I think it's supposed to be glued. Yeah, so I'm assuming if we that's been glued as well. It's got glue on it. Can you see the glue down there shining in the light? What is going on with this thing? And we've got something at this end here that's been glued in as well. Oh no, it just pops out, look. So it was glued and it is no longer. It's got an O-ring on it, rubber O-ring just here. and some more glue. So it's kind of a silicon slimy greasy thing going on. So I'm guessing that goes in there, and then this detail on the lid, look, on the actual base, you want to call it that, these lock these in, so they lock into this collar here. So when the lid goes on, there's a prongs that go down either side of that detail in the overmold on the cable that hold it in position. We just pull that, it should just come out, which it does. Pull this end, it should come out, which it does. And then is the electronics free to come out? It is. Never taken one of these apart before. So talk amongst yourself while I make a fool of myself. There we are. So there we go. So yeah, the Chinese battery chargers, Chinese from various places, have a plug on here, so you can actually free the electronics up from the case. But this has been hard sold. So to get maximum extension on this, I'm going to have to pull that out like that, and we can just about have a look at it side by side. This thing is probably a temperature sensor. Scrappy bit of sleeving on there. Can you see that? Oh, it's an LED. No, it's probably a thermistor for checking the temperature. It's obviously not a power component. It's too small. So what have we got? We've got an average FR4 type PCB, microcontroller, a button with a load spreader on the top, it's just glued on, I think. So tack switch for the mode selection. Power all up this end. Isolation here, 2 kV isolation between the low voltage side, which is the electrical connections which go out to the battery and the user can get connected to, and then an opto isolator between the secondary side and the power supply side to supply and modulate the PWM pulse generation on that chip. This is the management chip for the switch mode power supply. So anything obvious? Someone's been soldering that by the look of it. Might not be, but you never know. There's a mains fuse here, which is a normal fuse, which is, let's zoom in on that slightly, 2 amp 250 volt. Alright, so there's your 2 amp fuse. So I suppose the first next thing to do is check that fuse and see if it's blown. We'll see. I mean, if the power supply is working and the microcontroller is screwed, I think we're stuck on this. But hopefully, all things being equal, it'll be the power side that's causing us the grief. So check the fuse. You'll hear a peep. Mains fuse is good, right? So we've got a good mains fuse, but yeah, nothing else is working. Not plugged in at the moment, obviously. So what have we got here? We've got yeah, 4702. That can't be 47K, can it? What do they measure those things? I was wondering, 4702 normally says 47K, but if it was a number code, i.e. one of the coded resistors that has that weird table, they've usually got alpha, alphabet letters in the part number as well, or in the actual ident on the component. So let's just see what they are, see if they are 47K. It seems a bit low for a bootstrap supply resistor. Okay, we've got the controller out, let's have a look at it. So clearly you've got the microcontroller at this end, you've got the push button with a little load spreader on the end to spread the end of the small 3mm push button to make a reasonable sized button behind the control panel. Controller, micro, a comparator circuit probably, with some resistive comparators for the different voltage measurements. Clearly this micro needs to know what's going on. You've got the secondary of the transformer here, there's a smoothing capacitor, 2 smoothing capacitors in parallel, and they are 105-degree ones, vented ones, which is good. Caps on, never heard of them. 100 microfarad, 16 volt. Okay. I would like to have seen 20 volts in there, because this is going to be working up to 15.5. That's pretty close to the wire, but never mind. Then you've got your switching transformer. On the back of here you've got your 3-legged voltage reference, which drives into the optocoupler by a bit of driving circuit, and this is the optocoupler photodiode, infrared, 2 kV isolation, switching back and feeding back the supply voltage demands to the switch mode power supply pulse width modulation management chip. And if the voltage drops below, it turns the LED on, off, and if it needs more power, it turns the LED on and instructs this to push more power through to the other side to maintain the actual secondary low voltage DC. So this side is safe to touch because it's isolated. There should be a 2 kV isolation, except for these class Y capacitors, which are noise filtering capacitors. There's 2 on either side, and they're fail open, fail safe capacitors. Okay, so you should be able to put 2000 volts on this side and still touch this side with relatively small leakage, so it's a safety issue. Okay, but on this side, this is reference to the mains, so there's your live and neutral coming in. Bridge rectifier, 4 diodes arranged in a bridge, going around to a smoothing capacitor. Samson, how do you say that? 47 microfarad, 400 volt, which is reasonable, I suppose, a bit on the low side for the size power supply. And what have we got here? We've got the switching transformer, so that's the primary side of the transformer, and there's 2 windings on there by the look of it. One of them is the primary winding, and the other one is the bootstrap supply winding. I'll explain that in a minute, but it's a low voltage winding that when the thing has started up, it provides the DC power, the low voltage DC power to power the electronics. Okay, R47, 0.47 ohm resistor. Is that 47 or 0.47? R47, the R's in the front, so it's 0.470, so it's half ohm resistor basically, and a diode. What's the number on that diode, can you see? Yeah, so this is the snubber. The job of this is it's connected across the primary, and the job of it is that when you switch the FET off, the voltage will fly back, and it's to arrest the flyback, so it conducts and soaks up the over energy, otherwise the over voltage would damage the FET. And also, if it's quasi-resonant, which it probably isn't, it would you would adjust this to get maximum efficiency based on in conjunction with this capacitor here. Now that's a US1M. Yeah, that's probably a 1000 volt fast recovery diode. In this position, it would have to be a fast recovery diode, probably between 50 and 100 nanosecond recovery. If you put a standard recovery diode in there, it would lower the efficiency and cause a lot more heating in the primary. You want it to switch off. You want to do its thing, conduct, and then stop. When it on the overring, when it bounces back resonantly, you don't want that conducting, so it switches off quickly. Okay, so there's a snubber network diode. That resistor, that, and that capacitor make the tuned snubber for the primary. It improves efficiency and also helps to prevent the FET getting damaged. Now, down here we've got a rectifier diode. That's AC 0 volts, and that is the winding that goes through somewhere. There's a rectifier diode, I should think, for the bootstrap supply. Where is it? So one of these must be a diode, or some of these must be diodes. That one's a diode. Okay, so it comes down here through a diode, and yeah, it's a TO23 or 232 diode case, and then there's a capacitor in here, which is this one, which is, let's say, I can't see what the value is, 47 microfarad, 50 volt. So that's your bootstrap supply capacitor, right? And then somewhere also here is going to be on a current feedback resistor, which feeds back the actual current flowing in the primary back to the chip, so that if there is an overcurrent situation, i.e. there's too much current flowing in the FET, and bear in mind this might be going at 50 kilohertz, 50,000 times a second, if you switch the FET on and the current ramps up too high, then the network will detect that by generating a voltage across a low ohmage resistor somewhere on the current limiting and the soft start pin on this chip, which is a 1271. Yeah, 1271. So that's an NCP 1271 on semi chip, I think. Power supply management chip. I can't see where the current regulation is. It's on pin, one of these pins. Yeah, that's right. So that's the current sensing, because that's AC 0 volts. That's the path from the FET back to ground. So all the current going through the primary goes through that resistor. And then, so that is not part of the snubber network. This is the snubber, that capacitor and that diode is the snubber network. And so it comes down to there, and then there's to this feed, this track going off down here, goes through a 01B 1000 ohm resistor, and a capacitor, that's your soft start capacitor, going to this pin here, which is pin 3, which is probably the soft start current sense. Alright, so you've got a voltage sense demand pin, which this lot feeds back to through this opto-isolator to control demand for power supply. Then you've got this current sense resistor, not part of the snubber network, I was wrong, down through here, through this network here to there, and if you turn the FET on, there's too much current, then voltage, a threshold voltage applies to every device that I've seen, and if the peak voltage on here goes above, then this thing turns the FET off, because if it left the FET on, it would overcurrent the FET and you'd end up with a catastrophic failure. The caveat on that is you need some soft start, probably a capacitor or something, to get the thing going, because when you turn it on and the voltage comes on and the chip kicks into life, then the output capacitors on this side, the actual smoothing on the secondary side, are shorted, so there's quite a heavy load, and you have to charge those capacitors, so the voltage on the capacitors is low, so a lot more power than on average power demand is required to get the thing running to charge those caps up. So you have a soft start to ensure that you don't overcurrent the FET, because you start up slowly and charge them up, and whilst protecting the FET. And of course, if there's a short on this side, if there's a catastrophic short or something goes wrong on this side, then this will be driving too much power through the transformer, which means that the impedance of the transformer primary would be lower, which means more current flows through the FET, generating a voltage across its resistor to ground, because that's the return path of the FET to AC 0 volts, and then the voltage on here is produced, which is too high, which then turns it off. So that's how it works. What I can't see on here actually is 15, that's 1.5k. I can't see a bootstrap or a startup supply. Normally there's a high impedance resistor chain and a diode which takes the DC from the 260 volt line or 300 volt line through a resistor and a diode to a capacitor, which charges the capacitor up to a certain voltage, and when that voltage, the voltage across that capacitor, which is this one under here, I think the small one, provides the startup DC power supply for this to get started. And then when it hits a certain voltage, 12 volts or something, it will start working and run on the charge in the capacitor to get the first 50 clock cycles through the transformer. When the thing's up and running, there's a low voltage winding here which provides the actual running DC power, called the bootstrap supply, pulling yourself up by your own bootstraps. And there's more electronics here than would normally be expected, and there's a lot less protection electronics on the input than I would have expected. But nevertheless, what we're going to do, and we'll just poke about with it with the scope and see if we can spot whether it's working and what's happening. So let's zoom out a little bit so you can see that. You can see where I'm poking. And I'll turn the scope on and then we'll just do some measurement. What we do need though is, I'm running from an isolated supply, so at the back of my bench over there is an isolated AC supply, so when the wires come into the unit, live and neutral is not relevant. All there is 220 volts controlled by a variac as well, a variable transformer, 220 volts coming up here. Now I need to attach my scope and to debug this, but what I will do at the end, if you only have a DVM, we'll just go through some basic checks of what you can do with a DVM to ascertain what the problem most likely is. And I have actually got 2 of these to repair, sent in by someone from YouTube, as I said, and we can have a look at those and see what you can check and change with just a soldering iron to get yours working if it's broken. Alright, so I wouldn't recommend poking around with this with the power on unless you absolutely know what you're doing, and you won't be able to connect a scope probe to the 0 volt line on the high voltage side, because it'll effectively connect the earth on the scope to the neutral line, and if you've got an RCD, it'll blow out your RCD, or it could go bang. So okay, you don't do this unless you've got a isolation transformer with power on, I mean. And what we used to do back in the 70s and 80s was just to take the earth the earth lead off the scope and then connect it, then you could connect it. But it's not recommended, but you can do it. We used to do it, but now on health and safety you'd never get away with it. So what we're looking for is the negative line of the smoothing capacitor, the high voltage smoothing capacitor, which is that pin there. So that pin there is AC 0 volts. Right, so let's just solder a wire on that I can clip my scope onto. Power's off. That lovely solder joint. Right, okay, so the power is off. I have my 0 volts connected to my oscilloscope probe. Put some tape around it because I don't want that flopping over and shorting on anything. And let's move all this detritus off my bench, make sure the bench has got no bits of trimmings and wires on it, and let's see what we've got. So yeah, I'm just going to pull up the NCP 1271 datasheet. Let's go to Farnell, NCP 1271. Yeah, on semiconductor. Yeah, that's it. Scroll down a bit. Alright, so I'm referring to the circuit diagram a bit as well. It's on the screen to my right at the moment. So, but at the moment we're going to be looking at the scope and me fiddling about down here, and we'll refer back to the data sheet. My scope probe is on times 10. Maximum input to the scope is 300 volts. So the times 10 probe, I should be plenty okay not to damage my oscilloscope. Alright, so let's just fire everything up. Okay, we're up and running, I think, as far as I can tell. So I'm going to turn the power on. I'm going to stick just I'm going to put 150 volts on it just in case something goes bang. Oh yeah, I forgot to mention that on the live side of this, of the output of the isolation transformer, there's no connection to the mains copper wise, it's only through the flux in the transformer. I've got a 100 watt light bulb, one of these things, in a upright holder on the desk, just one of these, and the impedance of that is about 12, the resistance is about 20 ohms when it's cold, and if I short something out, instead of getting a huge explosion, all that happens is the light bulb comes on, and then when I'm confident it's working, I can switch the light bulb out of circuit, and then we've got full chat coming in. But for a small power supply like this, running on standby with no battery charging in this case, will be absolutely fine. Alright, so we're recording, yep, everything's going fine. What could possibly go wrong? Wait and see. Alright, so scope. So I suppose a few basic checks with the voltmeter to start with. Where are we? Let's just make sure we've got some power on this thing. I'll zoom out a little bit first so you can see. Sure nothing shorts out on anything. Right, you can just about see that meter, can't you? I think you can. Not the best meters. Actually, what I could do is go back to my good old trusty meter and use that. This thing served me well, it's been abused. Yeah. Good old fashioned LCD, works every time. Most of the time. Okay, so we should have that should be AC 0 volts on there, and that should be, turn it on first, turn it on, close your eyes, mother on speed dial, power on. Oh look, it's going up and down, that's interesting, so it is pulling some current. It's going down a lot actually, considering there's a 47 microfarad 400 volt capacitor on there. That's strange. Yeah, anyway, so we got voltage there. We can check on pin 6. You can see that pin 8 coming down from the high voltage supply on the schematic. So we'll just check. What I will do actually, before I do anything else, I'm just going to poke my ground lead of my meter in with the AC 0 volts connection here. There we go. So I've got the scope and the 0 volt lead of the voltmeter plugged in. Okay, so turn it back on, and so pin 8, which is this pin down here, let's move in. You can see it going up and down. That's the V in, that's the high voltage input. And VCC, which is pin 6, which is the DC power supply voltage for their chip to drive itself, low voltage DC. 9 volts. So it's stuck on 9 at the moment. I wonder if it's actually doing things. It might have something impressed upon it, but we can't see it because the meters don't respond. Yeah, so it's basically working. Well, basically the power is there. Now let's just see if there's any switching going on. So look on the scope, okay, and let's just see what the VCC is doing. So I can remove that, and I can move that over there. I can zoom in with this. Right, that should be good enough, I think, hopefully. Right, so we're looking at pin 6, which is the VCC. You can see it's wobbling about. Slow it down. Oh look, so there you go. Can you see that? I'm going to make that up a bit higher. There you go. So we're on horizontal 10 millimeters, so it's trying to start up. You can see the DC voltage on the VCC is climbing, which is the reservoir capacitor. The thing fires up. It gets no support from the bootstrap, and so it just runs down. So that's the capacitor next to the number 5 on the diagram discharging as the thing tries to start, and it's drawing charge out of the capacitor, but the cavalry, i.e. the bootstrap power supply, doesn't come and start this thing up. Interesting. I don't know if I can zoom in on that at all. It's probably not going to be that easy, but you can see that's what's actually happening on the VCC pin. So the chip, the controller chip, is trying to start the power supply, but it's not starting, right? Now if we look on the actual FET drive pin, which is pin 5, labelled DRV, pin 5, that's that pin there. God, it's don't want to short anything out. Right, there's the burst of pulses. You can see the amplitude reduces as it goes. Come on baby, you can do it. Put it on normal now. Come on, don't do this to me. Come on, what we need is a Technotronics, isn't it? There you go. Crikey. Those pulses are narrow. So we got 2 microseconds. So each pulse, it's going for half a microsecond, or a third of a microsecond, 300 nanoseconds, and then shutting down. So that's, to me, that looks like, if the FET is good, then that looks like it's current limiting. Yeah. So it's trying to start up. So we can see that it's trying to start. Okay, there's the burst of pulse. And it runs down to here until the voltage on the actual DC capacitor next to the number 5, low voltage decoupling capacitor, runs out of charge, and then it stops. Alright, so it's used up all the charge, so it shuts down, and charges. On this chip, I can see on the diagram, you can see there's a pin 8 is the high voltage connection. So on this chip there is no resistor, divider chain or rectifier. It goes straight into the chip at whatever the B plus voltage, 300 volts or whatever, and there's a constant current supply in there which derives the voltage, maybe 200 microamps or something like that, to charge the capacitor. Then when the bootstrap power supply comes on, that constant current supply is switched off. If you leave it switched on, it doesn't get very hot because it's got something like, say there's 250 or 300 volts on here, you've got 290 volts dropping across that device, so it's going to be dissipating a lot of power, okay? So it'll turn it off. But at the moment we've got no bootstrap because nothing's happening in the transformer. So then if we look at the data sheet for the NCP1271, it's here somewhere, there it is, and looking at the voltage limit on the feedback pin, which is pin 2, no, not feedback, current sense, pin 3, 1 volt. So the maximum primary current is limited to 1.0 volts. So if it goes over 1 volt, it's going to turn it off because it's too much current. So you set the value of this resistor for the peak current that the FET you want the FET to draw under normal operating conditions, and if the current in the primary raises above or goes above the actual safety limit, this will shut down. So let's just have a look. We're still on low voltage at the moment. We're on 5 volts per division. On the scope is pin 3. So let's just see what we've got on pin 3, which is there, which is also this point there, which is the 0 volts of the FETs, the low side of the FET. It's easy for me to probe. I want to probe on there and have a look. There you go. So there's the pulse. There's the pulses. Can you see the pulses on the scope? And if we speed that up, put it on normal, and we speed it up, and we have a look, turn the gain up, 2 volts. We've got 2 volts, so way over current. This pulse here, this positive rising pulse, should be less than 1 volt, otherwise this unit will shut down the power to the unit. So it's trying to start up, but there's too much current in the primary. Okay, so what could be causing too much current in the primary? So first of all, let's just make sure the FET is actually switching properly. If you had a very bad FET, it could cause this, but I'm going to put that on 150 volts per division at the moment, because I don't want to blow my scope up. Now I'm going to look on the actual high voltage side of the FET, which is this connection. Which connection? Think before you probe. Actually, let's look on the gate of the FET first to make sure the FET's been driven properly. So I'm going to turn that back down to 5 volts. There you go. And we'll look on the gate, which is this one, I think. That's 0 volts. So it's got to be this one. So there's the gate drive signal. Looks alright. You can see it driving. There's a bit of a rise on it. That's from the input capacitance, the gate of the FET, but it's 5 volts. It's doing what it's supposed to be doing. So it's being driven, right? So now I'm going to turn the gain of the scope right down so I don't overpower my scope. Let's go to 100 volts. So that's with the times 10 probes, that should be 1000 volts per division. Right, so that's the actual secondary, the bottom of the primary. The other end goes to the high voltage supply, and that's what we can see happening on there. Up to there. Normal. Okay. That is looking very slugged to me. There's no ringing or anything, it's completely dead, isn't it? You'd expect a transformer to have some overshoot, not much happening at all. You can see it's the same old burst that happened before. So I think we've ruled out the low voltage capacitor. Obviously the high voltage capacitor seems okay. If the high voltage capacitor was open circuit, you'd get some hum and some strange things happening, but the power supply usually generally works. And this is quite a young battery charger. So I'm thinking, what am I thinking at the moment? The FET seems alright. Okay, so we need to double check to see what's going on the secondary side. So if I just take the power off there, so I've turned the power off, and I'm going to quickly connect a 12 volt supply across the secondary of the unit to see if there's an overcurrent on the secondary side. If there's, on the low voltage side, if there was a short on here, it would basically short circuit the power supply and we'll be able to see overcurrent and failure to start up. So we need to rule out that this side is actually okay and isn't damaged. Okay, so what do we do? There we are. So we take our negative wire, which happens to be red. Couldn't find the right colour wires for this, guys, and just clip it onto the negative side of these two second. We're talking about clipping across these capacitors in here, which is the secondary DC smoothing capacitors. So we'll stick this is negative, highly unprofessional, don't tell anyone, and this is positive, and we'll set to 12 volts, and we'll set to start with, we'll set it to 50 milliamps, just in case there's anything nasty going on. And that's channel 1, so turn it on. Yep, so that's good. So turn channel 1 off, and okay, so the white is positive. That's right, I got it around the right way. Makes a change. Make sure it's not shorting on anything else. Not the probably ideal, but probably better ways to solder them on, but this will be good enough for what we want. Alright, so they are. There's them trapped on. So if I just turn the power on. Right, so we've got 12 volts in there and we've got 18 milliamps being drawn. Oh look, we've got some lights. Look. It's working. I'm not going to turn it on properly, but yeah, there's some life on the secondary side. So there's no short on the secondary side. So the overcurrent situation isn't coming from the secondary DC power consumption, alright? There's no short. So let's turn that off. Let's turn that off. Let's remove these connectors. So now we know this side isn't going to be a problem. If the main rectifier diode, which is that thing in there's two diodes in the same pack, was shorted, you'd get a short across the power supply, because it would actually be connecting. When I connect across here, it would be flowing through the shorted diode and through the primary winding of the transformer, which is probably about 15 or 20 turns of copper. So it's a hefty 5 amp winding on the secondary side, and so we'd see a short. So I don't think it's actual secondary diode, but in fact I rarely see the actual DC rectification diodes blowing up. They're very reliable for the low voltage rectification side. So going back to the primary, now what have we got now? We've got it doesn't appear to be the FET. It's turning on and off correctly, and the leaky FET or a poorly switching FET would manifest itself as a lot of heat actually, because it's switching 200 or 300 volts very fast, and if it's turning off or on slowly during the gradient of that slow turn on, it's acting as a resistor, and as it acts as a resistor, it's dissipating heat. Okay, the idea with the FET is to switch it on quickly and switch it off quickly. Then you only dissipate energy during the switching edge, and so the more of the slope of the steeper the switching edge, the faster the switching, the less power dissipation during switching. Then you've just got, during the fully switched on state, you've just got the resistance of the actual FET fully switched on, which is probably 100 milliohms or something, and dissipating power, and a lot of power in 100 milliohms requires a lot of current, which isn't present in this circuit. So hot switching transistors usually means they're damaged or not being driven correctly. Okay, this is a very simple circuit. So I'm thinking, yeah, well, unusual, but let's just try it. I'm thinking the actual snubber diode, actually, or the snubber circuit, this capacitor or that, has gone short. This is this 1000 volt fast switching diode. Power is off. Better discharge the actual capacitor to make sure I'm not doing anything stupid. Right. And so let's take this component off here. I'm going to lift. Oh, it's come off completely. Okay. No, it hasn't. Okay, remember the bar goes at the top, positive at the end. So here we have a snubber diode. Yeah, it's not shown on the circuit diagram, but it's a typical component. This is the 1000 volt fast switching diode, as you recall. Let's try it on the CTEK, because it's messy and it's technical. Right, okay, so come on baby, what are you going to do for us? So I'm going to put on Diode Continuity. This thing will indicate either the forward voltage drop or the resistance. It's a slightly intelligent setup, which is not fully appreciated. Ah dear. Spot meter auto. There we are. Can you see that diode? You can't, can you really? Let's turn that back on. You can more or less see it. Yeah, we're good. We're golden. Right. Oh, look at that. That should be reading nothing, so I'm reverse biasing, so it's shorted. Turn around the other way. Blown diode, boys. On the primary snubbing circuit. I'll show you it is in the diagram in a minute. Yeah, so that's that. That's what's wrong with that. It's a fast diode. I don't know if I've got any... question is, why is this blown up? So, unusual fault. But, having said that, there ain't no varistor in here. What a cheap and nasty and crappy design, honestly. I think it ought to be gold plated for the prices they charge for these things. So that diode's gone. Have I got any fast recovery diodes or not? Do you know what? I don't think I have. I'm going to root around. It's easy just to order some, but what I can do is have a look in my power supply box. Where is it? There she blows. There it is. I've got these boxes all full of components. This is switching power supplies and transistors, power amplifiers and stuff. What have we got? Okay, we've got a... what's the part number on that one? 1000 volts. An RGP10M, that's 1000 volt, but it's not a fast one. It's moderately fast, but not super fast. But I'll tell you what, it'll be, if we put just this leaded diode on, see that one? It's one I've hooked out of something else before, but it's I could check the spec, but I know it's not a fast recovery one, but it's reasonably fast, but it's not super hyper fast, or what they call it, recovery. I mean, the recovery means how quickly it switches off when you reverse the current. And the faster it switches off, the better, basically, in this situation. Right. We'll be okay at the moment, though, because we're not pulling any current out of the secondary except 50 milliamps, in which case, i.e. the battery clamps are not connected. Come on, get on there. Right, okay, so I'm not going to get any tidy soldering wards today, but you never know. Right, not shorting on anything, it's just tacked in there, you can see that. Don't judge me. But let's just see what happens now. Here's the lights. Let's see if she fires up. Anything else to check? Can you think of anything else I've forgotten? No, I can't either. Right, everybody. Here we go, contact. Bang! Made you look. Well, would you look at that? Would you look at that? Ta-da! It's the snubber diode's blown up. Blown up. We're pulling. I haven't got this power meter on at the moment, but yeah. Unusual fault. You can see it flickering a bit, can't you? As though the regulation's not quite right. What the voltage is on the secondary. Should just check it. See what she's pushing out. Oh no, it's not flickering for me, it's just flickering for you because it's beating with the shutter on the camera. Yeah, so that's what that is. But let's just check the voltage anyway, just for shits and giggles. Voltage. DC volts. And Whoop. There we go, you can see enough of that. .65. There you go. So that's it, boys. That's what's wrong with that. So yeah, let's put the lights back on. It's now working. Yeah. So when the diode was when the FET turned on, it was pulling the current all the way through that diode rather than through the primary transformer. It goes to show how good the fast switching current protection of these switch mode power supply management chips is, isn't it? Which shows you how good they are. They can actually turn it off mid-cycle in time to save the FET junction. But that's what's wrong with it. I'm going to have to order some diodes though, because I don't really feel comfortable. And I know what I'm going to do. I'm going to stick a 1300 volt diode in there instead of 1000, and I advise you to do the same, and then we'll take it from there. I'll show you a series of checks in the next video where you can do it with a voltmeter. So I've got another one down there, exactly the same. I don't know if it's got the same fault, but we'll, rather than making two very long videos, we'll make another short video which just shows the diagnostics, how you can fix it with just a voltmeter. Now these Mestechs are about 25 quid and they are excellent. You would have had to pay hundreds of pounds for a meter for this kind of performance a few years ago. Very good meter. So if you haven't got one of these, you're going to need a decent voltmeter to do anything at all on this and do any diagnostics that I'm going to show you. So be prepared to buy one, and if you're prepared to get yourself, even a 10 or 15 pound multimeter would do. And of course you need a soldering iron, but I'll show you how to repair them with the soldering iron on the next one. So that's that one fixed. I just need to put the correct diode in and the modification. Actually, we can modify it now, couldn't we? Put the safety components that are missing, which they didn't bother to put in for us at the factory. So we'll patch the box. Yeah, today's another day, and I've been giving this a bit of thought actually, and that's what's in there. That's the diode that was in there, USM 1M. I didn't mention before, but on these diodes, the reason I knew it was 1000 is the M. Yeah, so US 1M, and the M stands for 1000. And that's the one that's in there, this one. That's the Farnell order code. That's what I'm intending to put back in, which is as fast, super duper diode, more expensive obviously, but 1300 volts. But having slept on it a bit, I was thinking, from what I know, I'm wondering whether it was current or voltage that blew this diode up. So what we can do is have a quick look with our current probe, if I can find it. So this thing, it is a current probe. You slide that back like that and you put a conductor through, and then you can see the current that's being carried by that device. It's good for transient currents, you know, things that are varying. If you put a DC current through this, it would just roll off quickly because it's it needs to be an AC. It needs to be a current. Should I say a current that, that's varying with time. That's not constant with time. So a varying current will measure okay. So we could have a quick look at that diode just to see how much current is going through it, because if you think about it, that's a 1000 volt diode just destroyed itself. Here, this is where this one is patched in at the moment. and yet the FET is only a 600 volt FET. And if it is over voltage of what's coming in, then it's going to be a pretty nasty over voltage spike, which you would expect to kind of destroy the FET. So I'm wondering if there's some kind of intrinsic weakness in this snubber circuit here, which causes the problem. So it would be nice, wouldn't it, to just reverse engineer it a little bit and see whether it has been badly designed, or it is just an isolated failure of the component. So yeah, so the iron is on. Let's remove my patched in diode. Okay, so break a new one out of the packet. I've got a knife anywhere. Yeah, a kingdom for a knife. Come on, out you come. Sourdough bread on there, I've just been doing some baking. Lovely sourdough. Put it back in the bag. And what I'm going to do is just to mount it vertically on here so that I can put a current sensing wire on it as well. So we need a nice big blob of solder. Now of course 50 kilohertz, there is a small inductance associated with this current probe. So when you're using these current probes, you have to be mindful of the fact that you are introducing an extra piece of an extra element of induction, or inductance should I say, into the circuit, which is not totally ideal. But you know, it's like quantum mechanics. You observe a particle, you have an effect on it. Even a scope probe will affect a high impedance, high frequency signal because it loads the circuit. Yeah, so that's on there. It's on the right way around. We need to put a little loop of wire. I'm just going to put a little bit of single core wire in, enough to get my current probe onto the actual current path. 50 kilohertz, it won't be that significant. If this was 2 gigahertz, obviously it would be a complete non-starter. Even if it was megahertz, it would be a non-starter actually. Right, so when we let's turn the scope on, let it warm up. Not that there's any valves in there, but there are a couple of crystal ovens. Right, okay, so be careful clearly we don't need a ground connection on this, I don't think. Shouldn't need one. Alright, so we've got our current probe connected. Plug it into the scope. We'll make it 2 milliamps per millivolt. The gain switch. These are horrifically expensive. One of these is about £1,700, one of these current probes, so you have to treat them carefully. It takes a lot of the guesswork out of design and design validation though. Right, move that out of the way. Okay, so let's power is all connected, everything is safe, bench is clear. Right, let's get ready to turn on. I'll set up the scope and then we'll turn it on. Well, there's your problem. We're on 10 millivolts 10 milliamps per millivolt. Well, there's your problem. That's the current flowing in the snubber diode, and we're on 10 milliamps per millivolt, so we've got a trigger voltage. You can see it triggering there, and if I just turn the trigger up slightly, no. So 4.8 volts, so we've got a peak current in that diode 48 amps. The job of that diode is to conduct away the actually overshoot from the parasitic inductance from the transformer. The parasitic inductance is the stray inductance, which isn't coupled from the primary to the secondary, and the peak of that current, I know from experience, can vary widely on the quality of the windings of the transformer and how the transformer cores have been put together properly. But the diode, that's why it's blown up. It's not a mystery, it's overloaded. And I've looked at the application sheet for the 1291 chip, and you know, they're pushing, on this design it's 5 amps, about 14 volts, which is 70 watts, is that right? 5 times 14, yeah, 70 watts. So they're pushing 70 watts, and the limit for this in all the data sheets really is around about 40-45 watts. So they've squeezed every ounce of power they can out of this design. It presumably was for a previous inferior design at lower current, and they've just boosted the current, like they did at Boeing when they increased the thrust of the engine just by increasing the turbine blade size without trying testing it properly, and then they had to ground the engines until they sorted a problem out for the turbines. You can't just scale things up very easily. So we've got too much current flowing in that diode. That's the peak diode current, and if I just turn down the time base, you can see it's happening. That's when the FET switch is off, you get that overshoot on the transformer, and then the diode starts conducting to the resonant circuit. I'll show you in a moment the circuit on the screen. So the question is, I noticed that the current, if I just turn the voltage down, you can see it increases. As the voltage goes down to 200 volts, it gets much worse. So some remedial surgery is required here, boys. Yeah, overloaded diode, that's why it blew up. I'm guessing it's a common fault. Have I got time to investigate it? I'll do a little bit more on it. But the 1300 volt diodes are 20 amp full current, so they're not a good move. It's not voltage that's killing this, it's current. And in fact, the design only requires a 100 volt diode, but you can't get 100 volt rapid switch off diodes that will handle the current. Okay, so they've taken the diode on the data sheet and moved it to a 1000 volt 30 amp one, because obviously they're aware of this problem, but it's too marginal a design, and I don't know how long it will take for this one to blow up. There's no load on the actual power supply at the moment, except for the secondary, you know, the micro and the LEDs and that sort of thing running on it. So we've got a problem, and if I just stick another diode in, it will work for a while probably, and probably blow up again. And no mysteries there. I had a quick look at the second power supply I've got, and guess what? Exactly the same problem. So it's a common problem, so we need to find a modification which cuts down the stress on that diode. I'm surprised it's that high. There's something not right, probably about the transformer design. The FET is switching off on and off fine. The quality of that decoupling capacitor needs to be looked at as well. So there's a few things which I could play around with, but I don't have much time to get on with it really. As I say, I could put just another diode back in and send it back working, but I wouldn't expect it to be a reliable design. It's a design error in the actual power supply. I'm confident in my current probe. I've used it enough time in the past, and I've validated it all sorts of ways with series resistors and all sorts of things. It's well within the bandwidth of the current probe. So that decay you can see here is the actual snubber circuit, the diode conducting the transient power flying back out of the parasitic inductance on the transformer into a 22 nanofarad capacitor. I could reduce that capacitor and it will help somewhat, but you wouldn't get the same time constant of decay, and that's what we're looking for. We're looking for a peak current that's below the stress components, the stress levels of the components, and a peak current high enough to actually protect the output FET, and then a tank circuit which soaks up the transient in a time constant equivalent to the sort of series inductance and the duration of the flyback pulse. So we've got an overcurrent situation, not good. What should we do next? I'm going to think about this. Yeah, so anyway, look, the only other 5 amp battery charge that I've got is the Lidl one. I just had a look at the transformer in the Lidl £13 battery charge. You can see it on the screen now. Yeah, and the transformer is much beefier in the Lidl 5 amp for 15 quid than you get in a CTEK £60 battery charger. It's really underrated, and I'm wondering if it's actually saturating the core of the transformer, but there's a lot of stray inductance on this thing, so I'll have to think of a bodge before I send it back, something that's easy to do that will stop it failing. Anyways, I think that's a reasonable conclusion for this video. I'm going to think about how to modify this. You've seen what's wrong. You could put another diode back in and get your battery charger working again. Number 2 in this series, CTEK Repair, will be the modification. So if you're interested in how to modify your battery charger, stop it failing, then have a look. But it's an interesting conclusion for today, and I'm just going to upload this, otherwise this video just get way too long. So thanks for watching, and if you can look down in the corner of the screen down here and press the subscribe button and leave me a like, that would help to reward me for my efforts. I hope you found that interesting, and good luck with your